Hello, I'm David Pollard. Welcome to the Cambridge University Press webinar on our new book, Structural Geology, A Quantitative Introduction. Next slide. I'm Professor Emeritus in Geological Sciences at Stanford University. Just to give you a little background, I received a BA degree from Pomona College in 1965, where I was introduced to the classical side of structural geology by Donald McIntyre. I went then to Stanford University, where Arvid Johnson introduced me to geomechanics. And then I spent a year at Imperial College, University of London, working with John Ramsey on kinematics of deformation and with Neville Price on rock mechanics. I then went to the University of Rochester for a few years teaching structural geology, spent 10 years at the US Geological Survey working on earthquake problems, and from 1983 to the present have been at Stanford University. At Stanford, I taught an undergraduate course in structural geology from which this book emerged.
Okay, and I'm Steve Martel, and I'm also a professor emeritus in earth sciences, but at the University of Hawaii. In 1980, I got my BS in geology from UC Davis, and in 1984, I received my MS in engineering geology from Stanford, where Richard Johns was my advisor. In 1987, I got my PhD in geomechanics at Stanford with Dave as my advisor. And Dick Johns and Dave Pollard both played very important roles in my educational background. Dick introduced me to a systematic methodology for approaching problems in engineering geology, and Dave did the same thing with geomechanics through my PhD work. The year after I got out of Stanford, I worked at the Bureau of Economic Geology at UT Austin. I then worked for 4 years at Lawrence Berkeley Laboratory in a fracture hydrology group. And in 1992, I joined the University of Hawaii and migrated from assistant professor to full professor from 1992 to 2019. Most of my work at the University of Hawaii was applied research on faults, landslides, fractures, and topographic stresses. The primary courses I taught there were an undergraduate course in structural geology and an undergraduate course in engineering geology. And then in addition to service, one of the other major things I did at the university was work on the book with Dave, which was published last year.
So what inspired us to write this textbook? Steve and I wanted to teach a course with a textbook that actually used the prerequisites that many universities and colleges require for this upper division course for undergraduates in structural geology. And of course, that would include physical geology, largely a description of structures. It would include mathematics, that would be calculus, and physics, generally mechanics side of physics. So our objective was to include those prerequisite subjects in the textbook. We also really wanted to present what we would think of as a coherent theory of deformation, starting from first principles, the conservation laws of mass momentum, and ending with what we call canonical problems of classic geologic structures. We also wanted to promote what we refer to as quantitative analysis. That includes computer modeling, dynamic graphics to support thinking in 3D, and we've chosen MATLAB as the computational engine for that purpose. So how is the book structured? We wanted to structure this book in a way that would seem familiar to instructors at the undergraduate level. And we start with chapter 1, giving the scope of structural geology. What is it? There is then there are two chapters, one on the mathematical requirements and the second on the physical requirements for the book. That's a little bit unusual for an undergraduate book, but we really wanted to give people the flavor of what we were going to use and what the important aspects were of both the math and physics prerequisites. In part 3, we launch into the 3 chapters that discuss first the elastic brittle deformation, then elastic ductile deformation, and finally elastic viscous deformation. And you can see on the right here a chart which shows schematically the experimental result you might get testing rock samples, where the initial deformation is largely elastic, and then it can become either brittle or ductile. In the 4th part of the book, we take on the major classes of structures: fractures, faults, folds, fabrics, and intrusions. We cover each of those, including the canonical problems, which are introduced using the prerequisite math and physics, and lots of descriptive material so that people can see, as in that beautiful picture in the lower right, the kinds of things we see in outcrop and how do we interpret those. Just as an example, if you're thinking about designing your own course, this is the way it turned out for me at Stanford. You have to pick and choose. There's too much material in this book to really fit into a 1 semester, even a little more difficult in a 1 quarter course. And your own interests as an instructor may dictate your choices here. But what I did was to teach of the 11 chapters, really 9 of them, and include both brittle and viscous deformation. That's chapters 4 and 7. 6, and then give lectures on fractures, faults, and intrusions. If you have more interest or want to emphasize ductile deformation and fabrics, you might substitute chapters 5 and 9 for chapters 6 and 11. That is something that can be encompassed in a 10-week, 20-lecture course.
Okay, so the book has several pedagogical features that we emphasize. First, we try to set the students up to work with quantitative field data, and this could be, for example, data from global positioning systems or airborne laser swath mapping or LiDAR. And in many cases, these are large data sets that really can't be handled by means other than using a computer. Second thing is we wind up using calculus to explore how physical quantities such as stress, strain, displacement, and velocity, for example, vary with position and time. And this variation of physical quantities with position and time is different from what is done in many books, where there tends to be a focus on physical quantities at one single point. And calculus obviously plays a big role in looking at how physical quantities vary with position and time. We also show how to use MATLAB for data analysis, modeling, and for visualization, and it's very helpful in all those 3 areas. And then finally, the other point that's distinctive about the book is we introduce continuum mechanics and conservation laws, such as for mass, momentum, and energy, to provide this uniform theoretical basis that Dave alluded to a few minutes ago for investigating tectonic processes and the structures that result. One of the other things that's a little different here, and it deals with that word processes, we focus more on processes than on mere classification of geologic structures. So students who are interested in how would a fault develop, how do folds form, our book is directed to answer questions such as that. Next slide.
So if you open the book, you're very likely to see on almost every page an equation or 2. And I know students might look at that and panic. They might say, am I going to be required to memorize all these equations? And some of these seem to be mathematics that I didn't necessarily get in my undergraduate calculus course. Well, just to reassure you, there are some prerequisites. One would be the calculus for STEM majors, and that would be differential and integral calculus of 1 variable. But there is other mathematics we use, and we don't really consider that a student would need a prerequisite course in these things. For example, we use some quite elementary analytic geometry, a little bit of vector calculus, and some linear algebra. But what a student needs in order to use these in our textbook and with our textbook is material that we provide in the textbook, in chapter 2, or as we go along throughout the other chapters. You'll also notice that there are some partial derivatives and some gradients, things that would be part of a multivariate calculus course. But again, we use these at the most elementary level, and we introduce in the book itself what we feel students would need to understand in order to use them. The equations are there to be read, not memorized. And in fact, some of them are repeated often enough so a student might actually remember them, but that's not a requirement. They're an integral part of the story of deformation and the story of the development of structures. So they should be read just like the text and used to summarize what are, in some cases, pretty complicated physical concepts. So they're a condensation and a summary, and we use that notion to include them very much like the text itself. Next slide. In terms of the physics, again, there is a prerequisite, and that would be the undergraduate physics course for STEM majors, and in particular, the section of that course on mechanics. The problem here is that in that undergraduate physics course, the mechanics is usually focused on point masses and rigid bodies. And you learn a lot about the famous relationship that Newton came up with, the force is equal to the mass times the acceleration. But you really don't learn much about how you would deal with things as complicated as this shear zone that I show on the right, where quantities like the stress and the strain are varying from place to place. This is not a point mass. These are not rigid bodies. So what do? Well, you need some continuum mechanics. And that is generally not included in that undergraduate physics course. But again, what we do in the textbook is we introduce at the most elementary level those aspects of continuum mechanics that we're going to use. And we hope that the students will be motivated to understand these concepts and use them because they want to understand the physical processes that lead to the development of geologic structures. Now, the payoff here is immense because these concepts from continuum mechanics are applicable at all relevant length scales for structural geologists and all relevant time scales. And in fact, they apply to brittle, ductile, and viscous deformation. So they really cover the spectrum of things that we're interested in, whether it's at an outcrop or at the level of the Earth's crust, whether it's milliseconds or millions of years, and whether it's brittle, ductile, or viscous deformation. So we developed this quantitative analysis for the interpretation of geologic structures based on Cauchy's law of motion, which come from those conservation laws. Next slide. Here's an example I wanted to use to illustrate that these concepts, these physical concepts, apply over all the length scales we're interested in. These are amazing pictures from an SEM image of a single dislocation in silicon. And so we're looking down at the nanometer scale. You see the little scale bar there. And what you see in those bright colors are like contours of the displacements in the X and the Y direction. And if you compare from left to right across the top row, you see on the left the SEM image, and on the right what the continuum theory says the displacement contours should look like. And then in the lower two, you see again on the left the SEM image, and on the right the continuum theory. So here's an example that demonstrates that the continuum theory applies at near atomic scale. Next slide. let's jump all the way up to the crustal scale. If you look at the scale bar across the bottom, you see those are kilometers, from 520 on the left to 600 on the right. So we're looking at many tens of kilometers. And that little black line going across the center of the view on the left is in fact the fault from which the Hector Mine earthquake developed. So this is again, a contour map of displacements, in this case in the look direction of the satellite. So this is INSAR image. And on the right is the continuum theory. A model was developed, the displacements were calculated, the contours were computed, and you can see a remarkable similarity between those contours from the continuum theory and those from the INSAR image. So I hope this would convince students that it's worth the effort to learn the math and the physics to be able to understand deformation at scales that range from near atomic up to tens or hundreds of kilometers. Next.
Okay, now we don't just deal with data sets that might be developed from INSAR measurements or LiDAR measurements. We also wind up spending a fair bit of time addressing field observations and what one can deduce from them. So, for example, when we discuss faults in different kinds of rocks, crystal and granitic rocks, sedimentary rocks. In our discussion on the development of faults in granite, some of the questions that we ask are, how do faults grow in granites? Do they propagate as shear fractures or in some other way? Are the macroscopic and microscopic features of the faults related in any way or not? And what does the growth process that we can deduce imply for seismic processes along these faults? Next slide. Okay, so for the field area that we've done most of our work on, the faults, it's in the Sierra Nevada and California, and in particular in the Bear Creek drainage, which I'll refer to in a couple slides. And so the cartoon in beige shows some of the macroscopic developmental patterns that we've seen here. First, and this is shown on the left, a series of joints opened up. And the little opposing arrows that extend away from an individual joint trace show the relative motion of the walls of the joints. So these have no slip. The fractures first opened up. After that, faults developed as some of these pre-existing joints slipped. And these faults, which tend to range in trace length up to several tens of meters, have generally accumulated less than 10 meters of slip. The third stage is the development of fault zones, and these fault zones tend to accommodate 10 meters of slip or more. We've tracked as much as over 100 meters of slip on some of these, and these faults range in trace length from roughly 100 meters or so to about 10 kilometers. So the fault lengths, the largest ones, are great enough to potentially be seismogenic faults. The macroscopic features that we've seen along some of these faults tends to track what we see with the macroscopic aspects of the structures as well. The joints shown in the lower left diagram are opening mode cracks, and they contain euhedral or pristine crystals of quartz, chlorite, and epidote. Faults, which are shown in the second diagram, colored diagram, the central one, tend to have myelinitic fabrics involving quartz, chlorite, and epidote. And then fault zones, the boundary faults of the fault zones, shown in a thin section on the right, contain cladoclastic or brittly deformed quartz, chlorite, and epidote, along with some feldspar derived from the wall rock, as well as pseudotacholite, which is a quenched glass that geologists infer has developed as a result of seismic slip along faults. Next slide, please. So to help understand this sequence of development, we present a two-dimensional canonical model here. And the fault geometry is shown in diagram A. The faults have a trace length, which we call 2A, and this is a map view in figure A. There's a vertical extent, so this would be in and out of the page, that's much, much greater than that dimension A. The faults in our model have a vanishing thickness, and the faults are vertical. We also established a rheology, and in this case, we use linear elasticity, where the components of the stresses are proportional to the components of the strains. And we also introduced students to boundary value problems. So we set boundary conditions here, and there are two boundary conditions for this problem. There are remote boundary conditions, which are illustrated in the box in the upper right. And these show the stresses, for example, very far away from the center of the fault traces. In the diagram here, the superscript R's designate the remote boundary conditions. The superscript F denotes the boundary conditions along the fault. So if we take a look at the remote boundary conditions, and you can see these in the upper right-hand drawing, we designate the shear stress parallel to the fault with the letter S, the symbol S. We denote the normal stress that acts perpendicular to the fault as minus C. The C here could be understood to stand for compression. The magnitude of the compression, and the minus sign indicates this stress is compressive. And there'd also be a normal stress that's acting parallel to the fault. We don't know what this is, but we can try different values for this and see what comes up out of the models. For the conditions along the fault, there are two boundary conditions that we prescribe. One would be the shear stress on the fault, which we call R. It could be considered to be a resistance to slip. And then there would also be a normal stress perpendicular to the fault. And here that's minus C, the same value as the remote loading that's perpendicular to the fault. Next slide. Okay. So here we can wind up comparing some of the model predictions with what we actually observe in the field. In the model predictions, there are two diagrams. One, the upper left diagram shows the normal stress that's parallel to the fault. So this would be acting in a left-right direction here for right lateral slip. The diagram in the lower left shows the shear stress parallel to the fault. And we present the equations for these deformation fields, but the diagrams here illustrate the key points that we want to make fairly well. And one of the things that you can see in the upper left diagram for the normal stress parallel to the fault is there is an anti-symmetry in the first and second quadrants, second and third and fourth and first quadrants. And where the label sigma XX is shown in the beige box with the arrows, as a result of right lateral slip on the fault, there's a tension that winds up developing near the fault tip in that fourth quadrant. If we take a look at the shear stress parallel to the fault shown in the lower left, the shear stress drops near the fault in dark blue, but it increases out ahead of the fault. So one might expect, looking at these two diagrams, that if the fault's propagated as shear fractures, they would extend in the plane of the fault, whereas if something else happens, for example, suppose cracks open up, that they would develop anti-symmetrically around the faults, with cracks developing in, say, the first and third quadrants for left lateral faults, or the second and fourth quadrants for right lateral faults. We take a look at the field observations, and that's me closely inspecting the cracks near the end of the fault. We do indeed see cracks that strike oblique to the fault on one side of the fault, but not the other. And so the location and the general orientation of these secondary fractures near the fault tips is consistent with the fault developing, or as these pre-existing joints have slipped, with branching wing cracks developing near the fault ends, not as the fault's propagating in plane as shear fractures. Next slide, please. So if we try to put all this together and combine the field observations of these faults of Bear Creek with the canonical model, we've developed a story like this, that the faults originated as, not the faults, the initial joints originated as the plutons cooled, and this is some work that Stefan Bergbauer, one of my master's students and one of Dave's PhD students, this is some work Stefan and I did. So that's shown in the upper left beige diagram. First, the joints open up. Next, the faults slip. So the faults are reactivated joints. And then the third diagram in the upper row shows that some of these small faults wind up linking by these oblique secondary fractures, and that's how the faults grow. And the fault zones seem to have grown by a more pronounced linkage of these faults side to side. We've seen no evidence that the faults in the Sierra Nevada propagated as shear fractures. They seem to have propagated by this linking mechanism. Another thing that's very interesting is we've seen a corresponding difference in the microstructures in the faults. There's been a transition from a euhedral fabric in the joints to a myelinitic fabric in the small faults, which is then overprinted by a cataclastic fabric in the boundary faults of the fault zones. And those boundary faults of the fault zones have the pseudotachyllite, which has been interpreted to be a product of seismic slip. So this sequence here from the joints to the small faults to the fault zones seems like it's likely to reflect a transition from fault creep to seismogenic faults. And one of the things that we as geologists tend to emphasize to students is that faulting is very interesting because faults produce earthquakes. It appears that this example from Bear Creek in the Sierra Nevada shows this transition from fault creep to actual seismic slip on fossilized faults. Next slide.
Okay, thanks, Steve. Going back to the textbook in general, let's just point out a few of the resources that you as instructors are going to be able to use. Cambridge has done a marvelous job with the figures. They're all color. The maps, the graphs, the diagrams are in full color throughout. We also have a comprehensive symbol lookup table at the beginning of the book. So if you come across an equation or symbols in the text you don't understand, there's the place to go. Third, each chapter is developed in what I refer to as sonata form. There's an introduction, there's a development, and there's a recapitulation. So this helps with the learning process. In terms of enrichment materials, they're text boxes, and these include information about some of the high-tech instrumentation like GPS, ALSM, structure from motion, and others that structural geologists use in order to bring quantitative data back from the field. And also there are boxes that discuss what some of the disciplines are that structural geologists will find themselves relating to, the people in those other disciplines, from rock mechanics to engineering, geology to material science and others. So that gives students a little glimpse into the breadth of this subject and how it might be used to help solve multidisciplinary problems. At the end of each chapter, there are review questions. These address the expected learning outcomes, so you as an instructor and your students understand what Steve and I really felt that you should be getting from that chapter. So those questions are offered, and the answers basically lie in that chapter's text. Finally, each chapter has a further reading section for things that students can use to delve deeper into the subject. And at the end of the book, there's a reference list for the entire book and an index. And that index is correlated with the text itself, because every word or phrase that's in that index is highlighted in color in the text. So we hope all of these in-text resources will help you and your students use the book. Next, please. Steve?
Okay, in addition to what's in the book, Cambridge has also spent a considerable effort to providing resources online through the Cambridge University Press website. All the photographs and all the figures that we use in the book are available as either JPEGs or PowerPoint files for free. So instructors who want to assemble, say, a PowerPoint presentation and use some of the illustrations in the book, they can get them. All the MATLAB exercises in the book are available from Cambridge, both as Word and PDF files, and all the MATLAB scripts that we use for our exercises are available online, every one of them. Next slide, please. Now, as far as how our book differs from other textbooks that might be used for first course in structural geology, the topical coverage of our book is similar. As Dave mentioned earlier, we cover fractures, folds, faults, and fabrics, as well as igneous intrusions. So the topical coverage is similar. The main difference primarily is our approach. We try to balance the descriptions and analyses of structures, as most introductory books do, but we approach this from a quantitative standpoint as well as a qualitative standpoint, but we emphasize the quantitative approach. We also try to develop quantitative explanations for how geologic structures form based on physical principles as opposed to ad hoc reasoning. We try very hard to develop the quantitative and computational skills of students, and they're similar, but they're not the same thing. The computational skills are becoming more and more important, and we use MATLAB for that. We use things like calculus to understand, again, how physical quantities vary in space and time. So both those areas we develop. And then finally, we wind up drawing together observations, analysis, theory, and synthesis all together to develop a systematic methodology for how a student or professional might actually do structural geology. So the book hangs together and provides this systematic methodology that many students find very, very helpful to see how the various components of the material are all knit together into a coherent whole. Next slide. And at this point, we can take questions.
Yeah, that brings us to our question and answer period. So we're looking forward to hearing from you and addressing your questions. I'm going to just read the first question that's popped up. Is this book appropriate for single semester courses? I think the answer to that is yes. I've actually used it in a single quarter course, so even a shorter period of time, 10 weeks. A single semester should be quite adequate. I think that may be typical of how the undergraduate structure course is organized at many universities. You will have to pick and choose. As I said, the book contains more material than you probably would want to cover in a single semester course, but you can cover all the basic material and then perhaps pick and choose which structures you want to emphasize. I think it's quite a reasonable proposition to aim for a single semester course, but I wouldn't just start on page 1 and think you're going to get through every page in that course. Steve, do you have any comments on that?
The one thing I'd add on that is many schools, the background of the students and the required prerequisites and the use of the required prerequisites differ, and instructors may need to spend more or less time going through, say, review of the prerequisite mathematics and physics. When I taught my class at the University of Hawaii, I wound up having to dedicate 1 to 2 weeks for our students to review some of the mathematics and physics, and that came at the expense of some of the topical coverage of geologic structures. At other places, instructors may need to spend less time, possibly more time. So this gets back as part of the picking and choosing that Dave mentioned. It makes a big difference to know your students, to figure out just what's the right balance to present to them using the book.
That person has now responded, I believe, and said, thanks, do you think Python instead of MATLAB? Well, there'd be no objection to that. MATLAB is the tool that Steve and I have used. We do provide all the MATLAB scripts, and it certainly encompasses all the necessary tools that we need for this book. I would be tempted to suggest, although this really depends on your own interests, that you give MATLAB a try, because you have all these resources available that tie in with the computational exercises that are provided. But if you have students or yourself want to try to solve some of these problems using Python, go for it. You know, that's that's another way to treat it. But the resources really are there for using MATLAB. And there are a number of different ways you and your students can get access to MATLAB, including using the free online versions, which are out there. Steve?
Yeah, an example of the free versions of MATLAB would include Octave. So if instructors are thinking about Python primarily because there's not a charge for it and their institution may not have MATLAB, other alternatives exist to MATLAB. As far as we know, Octave runs the MATLAB scripts pretty seamlessly. So there is that option.
The next question is, can instructors use this book for advanced graduate courses? And of course, yes, you can, depending on what's happening at your institution. If this book is not being used as an undergraduate offering, it would be possible to pick it up and use it as a graduate offering. It's designed really for undergraduate students, but there are no rules against using it in a graduate course. You may want to pick and choose the material you use for a graduate course in a different way than you would for an undergraduate course. But if someone's had a classical training in structural geology, as I did at Pomona College, and then came to graduate school, as I did at Stanford, this book would have been a perfect way to introduce me to the quantitative aspects of structural geology.
I'd echo those same kind of points.
But then the next question is, would this book be appropriate for technical professionals, such as professional geoscientists, to use, or is this only for college students? Well, there certainly are things in this book that a professional, say in rock mechanics or in petroleum, structural geology or engineering geology, might find useful. It is organized as a textbook, so it's not like a reference manual in that sense, but it's certainly something that if I were working, say, in rock mechanics or in petroleum, I'd want to have it on my shelf. Very much like I had for years and to today, the rock mechanics book by Yeager and Cook sitting on my shelf in order to refer to that from time to time. So I think the answer would be yes. Steve, do you have anything to add to that?
Yeah, the kinds of things that many professionals, engineering geologists, for example, could benefit from are some of the relationships that we have for idealized situations. Again, these are some of the canonical models that we use. If there's a fault and its trace length is 10 kilometers, how much slip might there be on the fault? Somebody that's working on problems where they're interested in fluid flow through fractures might be interested in how wide might a fracture be given its trace length, because the aperture of the fracture plays a big role in how rapidly fluids would flow through. So even though these equations, again, are for idealized cases, which we think is appropriate for undergraduates, people in lots of different disciplines could use some of those relationships to develop some rules of thumb and a sense for how geologic systems operate from a mechanical standpoint that might be a little hard to come by in a lot of other books.
The next question is, how long are the review questions in each chapter? They're generally like a sentence or two. They're asking for the student to provide information about a particular topic, a particular concept. They're not questions that require computation. They're not questions that require one to write an essay. They would be a short answer that would hopefully indicate that the student had obtained from reading the chapter and studying it what the authors hoped they would learn. In terms of the computation now, the MATLAB exercises, which are available online, are much longer. There's something that might be assigned as a homework problem that might take several hours to complete. And so those are lengthy questions with quantitative answers and would require students to use mostly computation using MATLAB, but in some cases, other tools.
So one thing I'd add there, when Dave said that the questions could take several hours, that's not individual questions per se. Many of the exercises that are there have a series of questions where the answer to one can be used as to help guide the answer to the second, the third, the fourth. So we wind up walking students through what we think are some interesting exercises that require them to perform multiple steps. And one of the things on that point that I've noticed is many of the students that I've worked with at the University of Hawaii have been used to getting questions where they're one-step questions. So the questions tend to be that they've been exposed to tend to be very simple, and many of the students have sort of developed this sense that, well, the answers should be simple, and the whole notion that problems can involve multiple steps and one needs to see how to break down a problem and take the problems a step at a time. I think the exercises that we've got in the book provide students with some big benefits for being able to attack multi-step problems.
Right. Those would be the online. Those would be the online exercises predominantly. The ones that are at the end of each chapter would probably be quite suitable to use to open discussions in your classroom or to have the students respond to with just short answers, either verbally or on a piece of paper. So they're that type of question. Okay. The next question is, are there specific chapters I should focus on for one semester introductory courses? In the preface to the book, I present the way I organized the course at Stanford for the 1/4 course. And I would just refer to that, but also just look at the chapter headings and decide how you want to work through this. How many lectures do you have? How much time you're going to devote to each one? You know, I always found myself eager to try more things than, in fact, was possible in a 1/4 course. But you may take a year or two experience teaching this once or twice before you develop what you think is a comfortable set of materials for your classes. But there are those examples in the preface that would give you a clue, at least how I did it.
One of the things that I did in the class at the University of Hawaii is I made sure that the students got out on a weekend field trip for the class, and we would go over to the Big Island of Hawaii. And the geologic structures around Kilauea volcano are varied, active, and real jaw droppers. And so I tended to, in my course, I tended to pick topics that I covered that I knew the students would be able to see on the field trip. And so that worked out very well for me, and the students really appreciated this. They'd tell me this every single year, that the field trip really helped bring things together, and it now became crystal clear to them why the material that I covered in the lectures was what I covered. So I think it really makes a very nice combination when the material in the book can be paired with things that students might be able to see on field trips.
Okay, the next question is, how is this book different from the book Structural Geology of Rocks and Regions by Davis? I'm familiar with that book, and actually with all the other structure books that are out there. And our book, you're going to see when you open it up, is quite different in some respects, and really not very different in others. And Steve tried to highlight those in his last slide. But the main difference, I think, is, or differences are, we use the prerequisites. That is, we actually use the physics and the math that the students are asked to take before they take this course. We try to strike a balance between description and analysis that I think is quite unique relative to those other books, which tend to be more descriptive, more taxonomic, less quantitative, less focused on the origins of the structures, how they formed, what is the physical process. So you'll see in the book by Davis, for example, the mathematics is not used in terms of developing an understanding for the physics. Things are not derived from first principles, and then not illustrated in a way that relates them directly to the observational material that's presented. So those books that are out there, including the book by Fossum that Cambridge publishes, are there. They're beautiful books in many respects, but they serve a different purpose, and they weren't really satisfactory for what Steve and I wanted to use for our courses. So take a look and see what you think. I think you're going to find that students may be challenged a bit by this book in terms of the math and the physics, but if they really have a innate interest in structural geology and the curiosity about those structures, I hope they'll find that this provides real answers based on real physics.
Another big difference between our book and this, well, just about any other one that Dave and I are familiar with, is having MATLAB in there for the students doing computations. And because the scripts and all the figures are available through Cambridge, if a student, especially if the student's got some reservations about using MATLAB, they haven't used it before, the figures show what the equations should produce. And the scripts that we provide allow the students to do that. In many cases, it's simply a matter of clicking on a run button in MATLAB, and pow, they can produce these beautiful figures all on their own. And we try to introduce this in a non-intimidating way and provide plenty of examples for how students can use computers to gain insight into geologic structures. And our experience, both of ours, is that this has been pretty well received by the students.
The next question, is there an eBook version of this book? And I believe the answer to that is yes. I refer you to the Cambridge website in order to find out the details about that. And in fact, I've just seen a message, please email higher education, that's one word, at cambridge.org for any questions on the book copies itself. And there you can find information about the ebook versus the hard copy. Thank you. Okay, it looks like we're going to wrap this up. We've enjoyed doing this. I hope, despite the fact that we can't see you, that you also enjoyed this experience, and we'll take a look at the book. And Steve, you want a last comment here?
Well, one last question popped up that we're waiting to see what it is. So
Oh,
Dave,
right. This book and an advanced version of the Fundamentals of Structural Geology. Well, you know, 15 years ago, Ray Fletcher and I published a book with Cambridge on really an advanced course in structural geology. That was not designed as a book that would be used for undergraduate teaching, and did not have the resources that we've now included here. And this book is specifically designed for that undergraduate teaching, although, as we said, it could be used for a graduate course as well. So thanks for asking about that book, but if you're involved in active teaching today, I would say take a look at this one. The color that's used, all the resources in the text and online are just, I think, going to be really helpful for you. And so we're putting our effort behind this one.
thanks for everybody for attending. It sounds like we've dealt with the questions, and hope everybody's doing fine and staying safe and healthy.